Good evening, all of you, and here is a beautiful problem motivated by G Advance. So, in this problem, we need to discuss the discontinuity of I theta, where I theta is given as. Clearly, in order to appreciate the problem, we can play with theta a little bit. So, let's say if I keep theta equals 0, so corresponding to theta equals 0, I'll get I0 equals minus 1 to 1, 0 dx, and which gives 0 as the answer. Let's take one other case. Let's say I of pi by 2. So for theta equals pi over 2, the given integrals is dressed in the fashion of dx by 1 plus x square, and that gives tan inverse x evaluated from minus 1 to 1, which is pi by 4 into 2, which goes to pi over 2. So like this, clearly we can find the value at the known angles. But what if the angle is not known to us? Okay, so one way of evaluating this is usually using the well-known technique of King's rule, where we have a plus b f dx is same as integral of a to b f of a plus b minus x dx, and this you can easily prove nicely with the geometrical argument, right? But here I am going to take a simple substitution. So clearly we can see the given integration is dependent on theta, so it will be independent of x. So first I'll plug sine theta out, so I'll write I theta as sine theta integral minus 1 to 1 dx over 1 minus 2x cos theta plus x square. Now x square minus 2x cos theta motivates me to bring cos square theta into picture. Cos square theta motivates me further to bring sin square theta into picture, because one can be written very nicely with cos square theta I'll add and cos square theta will subtract, and now I can club 1 minus cos square theta, and the integration take the format of dx over 1 minus cos square theta is sin square theta, and the remaining goes to x minus cos theta whole square. That you can easily sense from here, because this part will give me x minus cos theta whole square, and this engages with sin square theta. And now we have a typical substitution over here. So I'll make x minus cos theta as some, let's say, u. So that gives me dx equals du, because anyway we are differentiating with respect to x for a particular theta, for a particular instant. So the given integration takes minus 1 minus cos theta to 1 minus cos theta, it's sin theta du over u square plus sin square theta. And now this is not very difficult, because you can clearly see it's x square plus a square kind of integration. So where again I can divide by u by sin theta and take that t. So directly this integral is going to be tan inverse u by sin theta and times 1 by sin theta. So 1 by sin theta will get cancelled with the sin theta, and this will be the integration that we'll have in evaluated from this entire chunk will be evaluated from minus 1 minus cos theta to 1 minus cos theta. So if I plug these two values in this given expression, what I'm gonna get is tan inverse 1 minus cos theta over sin theta minus tan inverse minus 1 minus cos theta over sin theta. Clearly this is valid if sin theta is not 0. So now taking theta equals, let's say, 0 or pi by 2 here. So separately we can find it. Now this we can further manipulate. 1 minus cos can be written as 2 sin square theta over 2 divided by sin theta can be broken down to 2 sin theta over 2 cos theta over 2. And the other expression can be written as minus 2 cos square theta over 2 by 2 sin theta over 2 cos theta by 2 by the basic trigo identity. And now we can cancel 2 sin theta over 2 from both sides, 2 cos theta over 2 from both sides. So first expression goes tan inverse tan theta over 2 minus tan inverse minus cot theta over 2. So it's better if you can convert the second expression also in tan of something. So there are many ways of converting. You can write minus cot theta by 2 as 10 pi by 2 plus theta by 2, or minus 10 pi by 2 minus theta by 2. Whatever you do, everything will converge to the same answer. So let's say right. Now from here, many students does common mistake, because directly they'll write this as, you know, 10 theta over 2, and this will be written as pi by 2 minus theta over 2, and that will give you the answer minus pi by 2. Always it fills from 0 to 2 pi, and that's clearly wrong, because you can write this only under this principal restrictions. Okay, so from here, since we already know the restrictions on, since we already know the restrictions of tan inverse, so I know this quantity can be written as theta over 2 or pi by 2 plus theta over 2 if and only if it is in the principal domain, because we can recall tan inverse theta belongs to minus pi over 2 pi over 2. Even graphically, tan inverse x versus x graph if I take, so let's take tan inverse x versus x at x 0 0. At x infinity, it will saturate to pi over 2. This boundary at x minus infinity being an odd function, it will be symmetric or origin, and it will go to minus pi over 2. So यहाँ से you can see, like, none of the answer of here, none of these answers will cross this window of minus pi over 2 to pi over 2. So now that gives motivation to think of the graph of tan inverse tan x, and it's not very difficult, because you can see this is periodic with pi, because tan x is gonna same be tan of pi plus x. Just I can draw the graph in the interval of, okay, so tan inverse tan x versus x, I can draw the graph in the interval of 0 to pi. So let's take 3 special point. So at 0 is 0, at pi over 2 the value is going to be pi over 2, so then will look like this. As infinity, little bit more than pi by 2, and the graph will look like this. This is tan inverse tan x graph. And from the graph, one can clearly see if the value of x is lying from the window of minus pi over 2 to pi over 2, then I can write the given expression tan inverse tan x will behave like x. If the value is lying from pi by 2 to 3 pi over 2, now this line equation, if I take, let's say, any input x over here, so this gap is gonna be x minus pi, and the height is x minus pi. So this equation is y equal to x minus pi, right? So tan inverse tan x will behave like x minus pi. Similarly, you can find the interval in which the other function behavior depends, right? So taking all these into consideration, now I'm ready to hit its head, because this quantity can be further simplified and it can be written in this form, right? So for theta equal to 0, I theta is already 0, because I 0 we have calculated. If I take theta belonging to 0 to pi, so under this restriction, 0 to pi we have 10 of theta by 2, so it's going to 0 to pi over 2, and that will give theta over 2. What about this guarantees? So if theta is 0 to pi, theta by 2 is belonging to 0 to pi over 2. So if I'll add pi over 2 here, so this input pi by 2 plus theta by 2 belongs to pi by 2 to pi. And in pi by 2 to pi, you can clearly see the equation is going to be x minus pi, right? So what is the value over here? It's minus of x pi by 2 plus theta by 2 minus pi, and which gives me the value of theta by 2 minus theta by 2 minus theta by 2 and minus pi over 2, which gives me pi over 2 adjacent. And that's very interesting, like in 0 to pi you'll get pi over 2. Now what is the value at I pi? Okay, so the value when theta equals pi, that we have separately calculated, it's 0. Again, if theta belongs to, let's say, pi to 2 pi, so in pi to 2 pi interval I can calculate I theta. The first bracket is going to be minus of pi minus x, minus of pi minus theta over 2, and the second bracket that you can check is theta over 2 minus pi over 2, and that gives me theta over 2 minus pi minus theta over 2 plus pi by 2, and this gets cancelled. We have minus pi over 2 as the answer. Right, now in the third window, this is that, and at theta equal to 2 pi, we already know the answer is 0. So clubbing together all the information, now I am finally equipped with I theta value. So I theta behavior is 0 for theta equals 0. It behaves at pi by 2 for theta belonging to 0 to pi. At theta equals pi, the value is back to 0. At theta belonging to pi to 2 pi, in this interval, we are having this minus pi over 2, and it's back to 0 at theta equals 2 pi. So this is how I theta versus theta will look like. You can also visualize this geometrically. So let me plug I theta versus theta geometrically in the interval 0, pi over 2, pi, 3 pi over 2, and 2 pi. So at 0 we have 0, between 0 to pi we have pi over 2, at pi it's back to 0, and then we have minus pi over 2, and at 2 pi is back to 0. So the number of point of discontinuity, as you can clearly see from the graph, is discontinuous at 0, discontinuous at pi, and discontinuous at 2 pi. And this is also the point of non-differentiability of this function. Further, if the question also asks of integration of 0 to 2 pi, I theta d theta in case, so that can also be done over here, right? Because 0 to pi will have this area, it's pi into pi over 2, and minus pi to 2 pi we have pi to 2 pi will have area as this distance is minus pi over 2 into pi. So this integration will die because it's kind of symmetric about pi. Alright. So many questions could have been asked here, and still the number of points of discontinuity is going to be 3, and 3 is also the point of non-differentiability. So hence I can tell the given function is discontinuous at 3 points and is non-differentiable at 3 points as well. Let's take another question, and this is again a very surprising result that we will get with the second questions with a smart substitution. So here is a question for you. We need to integrate half to 2 ln x by 1 plus x square. Now clearly the first thought process that will be is maybe you can use integration by parts. So I can take thought number 1. Ln x as first function, we'll try integrating the second one, minus derivative of first one, which is 1 by x, and then integration of that is tan inverse x dx. Again, tan inverse x by x, probably you can take tan inverse x as some theta, so we'll get theta by tan theta, right? And since x is tan theta, so dx is secant square theta d theta. Now tan you can write as sin by cos, so it's basically theta cot theta d theta, and then probably you can again use integration of parts. Okay, so it will be ln x tan inverse x, that evaluated from half to 2, and rest again it can be taken care of. But there is a smart technique of doing this. Now clearly method 2 will be, thought process 2 will be to use King's rule, but King's rule will not work here properly, because if I'll replace x with a plus b minus x, which is 2 plus half minus x, you can clearly see there is no symmetricity in the problem that's getting developed, right? So that straightforward, defends the use of King's rule. So here we can't apply. But what is worth noticing here is these integration limits. So you can see these integration limits are not symmetric at origin. So clearly if it is 0, sometimes when we'll have 1 minus 1 to 1, or let's say minus Golu to Golu. If this kind of a structure is there, so the first idea is to apply integral f is integral a plus b minus x, which we call King's rule in the coaching environment, right? But here we can come with another kind of beautiful substitution, because half and 2 is inverse of each other, right? So that is reciprocal of each other. So that motivates me to take a substitution u equals 1 by x. Now what advantage I'll get? Half will become 2 and 2 will become half, and maybe we expect something great happening. So until you do it, you can't recognize. So u equal to half is going to give me 2 to half ln 1 by u by 1 plus 1 by us square, and dx is minus 1 by us square du. And this is fun because it's 2 to half minus, we have ln u, because this can be written as minus ln u, right? So minus ln u and minus is going to become plus, divided by us square. If I multiply, is us square plus 1. And very surprisingly, you can see we got the same kind of a structure. Okay, and this quantity can be written as minus a half to 2 ln x by x square plus 1 dx. It doesn't matter whether you replace u with x, because basically if I have x dx from 0 to 1, the answer is half. And it's same as 0 to 1, u do u. So u is working as a, just a dummy variable. So it doesn't matter what you put here. So you put hash d hash, okay, and it's running from 0 to 1, both will be the same. And we have switched the role of limits here from a to b, a to b, minus b to a, because anyway you are, if I'm integrating a to b some function f of x dx, that's giving me capital psi b minus psi a, where psi is the antiderivative of this. So clearly b to a f of x dx will give me psi a minus psi b, provided the function little f is integrable. Okay, and this is nothing but minus I, and very surprisingly, you see I started with I and we got minus I, so that gives 2I equals 0, and the integral is nothing but simply 0, and that's very surprising answer. Now just to give you a feel of this answer, does it really make sense? How it can be 0? Because some of you might feel like ln x by 1 plus x square is positive quantity. In fact, it's not positive, because we have to draw the graph from half to 2, and you can see at x equals 1, this function, if I call this as f of x, and if you draw the graph, it makes sense. Area will cancel each other. Where at 1 is going to be 0, at 2 we'll have something positive, so we'll have some positive area and some negative area over here, right? And it will be kind of symmetricity about 1 will be developed, right? So whatever area we are having over here, symmetricity in terms of area, okay? So whether f of 1 plus x will be equal to f of 1 minus x, that we can't guarantee over here. But what we know, with the scaling factor, whatever area is there, that is de-scaled, and these sums eat each other. So positive and negative guys cancel each other, and we get 0 as the answer. So remember, whenever you have reciprocal in the limit of integration, you can always use this substitution to target J problem. Right. In the next section, I'll come with again some beautiful problem, and please do like and subscribe the channel, because आप video देख लेते हो और subscribe नहीं करते हो, तो it's fine, but mostly it will be useful for you, okay? Because this kind of good problems with detailed explanation will not be available usually in your coaching materials. Thank you. Have a good day.